Now, after studying the 5 metallurgical processes, let us discuss the extraction of few metals. First, let us see the extraction of iron. Extraction of iron. The chief ore of iron is hematite. The formula of hematite is Fe2O3. So, iron is extracted from the ore hematite, that is Fe2O3. Now, the oxide ores of iron, that is hematite, after concentration by calcination is mixed with limestone and coke and fed into blast furnace from top, and hot air is blown from bottom of furnace and coke is burned to give temperature up to 2200 Kelvin in the lower part. The burning of coke therefore supplies most of the heat required in the process. The carbon monoxide and heat moves to the upper part of the furnace, and in the upper part the temperature is lower and iron oxides coming from top are reduced in steps to FeO. Thus, reduction of iron oxide takes place in different temperature range. So, the apparatus used for the extraction of iron is called blast furnace, and this is the diagram of a blast furnace. And you can see in the blast furnace from the top, iron ore plus coke, that is carbon, plus limestone, that is calcium carbonate, is fed into the furnace, and a hot blast of air is blown from the bottom of the furnace. So, you can see at the bottom of the furnace the temperature is very high, and in the upper part of the furnace the temperature is low. And we can see that certain reactions take place, or reactions take place at different temperature ranges inside the blast furnace. So, let us see the reactions taking place inside the blast furnace at lower temperature range and higher temperature range. Now, the reactions in blast furnace at lower temperature range, that is 500 to 800 Kelvin. The reactions taking place are reduction of Fe2O3 using carbon monoxide. So, we know that in lower temperature range carbon monoxide acts as a good reducing agent. So, Fe2O3 is added into the blast furnace, it gets reduced to Fe3O4. Now, Fe3O4 form will again get reduced to iron, then Fe2O3 will get reduced to FeO. So, these are the different reactions taking place in the lower temperature range inside the blast furnace. That is, in the blast furnace, in the lower temperature range, the reduction of iron oxide into different oxides take place, and that is done with the help of carbon monoxide as reducing agent. So, these are the 3 reactions taking place in the lower temperature range. Here we get iron oxide FeO, Fe3O4, etc. Now, the reactions in higher temperature range inside the blast furnace, that is the higher temperature range is 900 to 1500 Kelvin. This is the higher temperature range. And we have fed into the blast furnace iron ore with carbon and limestone. So, in the higher temperature range, the carbon will get oxidized to carbon monoxide, then FeO produced in the lower temperature range will get reduced to iron, then we have fed the limestone, that is calcium carbonate. Now, here the limestone is added as a flux. So, limestone will decompose into calcium oxide and carbon dioxide, and calcium oxide will combine with silica, which is the impurity present, to form the slag, that is calcium silicate. Now, again carbon added will combine with oxygen to form carbon dioxide, and iron oxide FeO will combine with carbon to form iron plus carbon monoxide. So, here you can see in higher temperature range, it is the carbon which acts as the reducing agent, and it helps in the reduction of FeO to Fe plus Cu. So, these are the different reactions taking place in higher temperature range in blast furnace, that is 900 to 1500 Kelvin. The formation of iron metal, decomposition of limestone into CaO, which then combines with silica to form slag calcium silicate. And the iron that we get from blast furnace is called pig iron. It is obtained in molten form, and pig iron contains 4% carbon. Now, this pig iron can be cast into variety of shapes. So, next let us see what is the difference between pig iron and cast iron. The main difference is in the carbon content. Pig iron contains 4% carbon, whereas cast iron contains 3% carbon. And the preparation of pig iron is by the reduction of Fe2O3 with coke in blast furnace, that is the extraction of iron. And the extraction or preparation of cast iron is, it is made by melting pig iron with scrap iron and coke using hot air blast. And both pig iron and cast iron is extremely hard and brittle. So, these are the different forms of iron which differ in carbon content. The iron that we get from blast furnace is pig iron, and pig iron can be cast into a variety of shapes called cast iron. Now, next is another form of iron called wrought iron, WROUGHT, wrought iron or malleable iron. Wrought iron or malleable iron is the purest form of iron. Means the carbon content in wrought iron is very less. Now, how is wrought iron prepared? Wrought iron is prepared from cast iron by oxidizing impurities in a reverberatory furnace lined with hematite, and the hematite oxidizes carbon to carbon monoxide. So, I am writing the equation. The equation is Fe2O3 plus 3 carbon. Here carbon acts as a reducing agent. You get wrought iron plus carbon monoxide. So, this is the extraction of iron and different forms of iron: pig iron, cast iron and wrought iron. And wrought iron is the purest form of iron. Now, the second extraction is extraction of zinc from zinc blend. Zinc blend formula is zinc sulfide. This is zinc blend. Now, first zinc sulfide is converted to zinc oxide by roasting. So, the equation is zinc sulfide plus 3O2. Roasting means heating in the presence of air, gives 2ZNO plus 2SO2. Now, in the next step, zinc oxide is mixed with coke and heated to 1673 Kelvin. Here coke acts as a reducing agent, that is carbon acts as a reducing agent. So, the second equation is zinc oxide plus carbon at 1673 Kelvin, we get zinc plus carbon monoxide, and here carbon acts as the reducing agent. Now, the zinc metal obtained is distilled off and collected by rapid chilling. And to get pure zinc, the refining method used is electrolytic refining. So, this is the extraction of zinc from zinc blend. Now, next is the extraction of chlorine and sodium. Extraction of chlorine and sodium. First, let's see the extraction of sodium. Now, this extraction we have already discussed in the chapter electrochemistry. That is, sodium is extracted by the electrolysis of molten sodium chloride. So, the extraction process is electrolysis of molten sodium chloride. And in the electrolysis of molten sodium chloride, we get sodium deposited at cathode. So, I want you to refer the electrolysis in the chapter electrochemistry. Now next is extraction of chlorine. Now chlorine is extracted by the electrolysis of molten sodium chloride or aqueous sodium chloride. Electrolysis of molten sodium chloride or aqueous sodium chloride. Now in both the cases we get chlorine gas evolved at anode. So again I want you to refer the chapter electrochemistry to study the electrolysis of sodium chloride, molten and aqueous sodium chloride. So the extraction of sodium and chlorine. Now next is the extraction of aluminium metal from bauxite. And this process is also called Hall-Héroult process. This is an electrolysis process. So extraction of aluminium or Hall-Héroult process. So here the anode taken is graphite and cathode is steel. Anode graphite, cathode steel, and the electrolyte taken is molten aluminium oxide mixed with cryolite and CaF2. That is electrolyte taken here is molten Al2O3 with cryolite, and the formula of cryolite is Na3Al(F6) plus calcium fluoride. Now the purpose of adding this mixture, that is Na3Al(F6) and calcium fluoride, is to lower the melting point of the mixture, and it also helps to increase the conductivity of the mixture. So to lower the melting point of the mix and to increase the conductivity, we add cryolite during the extraction of aluminium. And anode used is graphite and cathode is steel. Now let us see the reactions taking place at anode, cathode and overall reaction. Now the reaction at cathode, we know that at cathode reduction takes place. So the reaction at cathode is reduction of aluminium Al3 plus, it is in the molten state. So you have to write the word melt plus reduction 3 electron, you get aluminium in liquid form. Now at anode, now we know that the anode taken is graphite. So at anode oxygen gas is actually liberated. But what happens is that since the anode is graphite, that is carbon, the oxygen liberated at anode will combine with carbon to form carbon dioxide. So during this electrolysis of alumina, we have to replace anode from time to time because anode is being used up. That carbon anode will combine with oxygen and it is removed as carbon dioxide. So the reaction at anode will be carbon, that is the electrode anode, plus oxide ion O2 minus from the melt will give carbon monoxide gas plus 2 electron. This is oxidation. Then again, so carbon can change to carbon monoxide as well as carbon dioxide. So carbon plus 2O2 minus melt will give carbon dioxide gas plus 4 electron. Now when you write the overall reaction is 2Al2O3 plus 3C. So here carbon acts as the reducing agent. You will get 4Al plus 3CO2. So So you can see in the Hall-Héroult process, aluminium is produced at cathode, and the anode we have oxygen gas liberated, but oxygen gas produced at anode will combine with carbon anode and we get carbon dioxide gas. And the overall reaction will be the reduction of Al2O3 with carbon, giving aluminium and carbon dioxide. So this is the aluminium, extraction of aluminium from bauxite, Al2O3. Now next is extraction of gold and silver. Gold and silver is extracted by hydrometallurgy or cyanide process or leaching, which I have already discussed. And the chief ore of silver is silver glance, and the formula of silver glance is Ag2S. Now, you know how it is done, the cyanide process for the extraction of gold and silver or leaching. And we can say that I am writing the equations on the board. 4A with gold I am writing the equation, plus 8Cn minus plus 2H2O plus O2 gives 4AuCN twice minus plus 4OH minus. Now next is 2AuCN twice minus plus Zn gives 2Au plus ZnCN 4 times 2 minus. Now you can see that this is the reaction. The first equation is dissolving gold in sodium cyanide to get a complex. Second is replacement of gold with more electropositive metal zinc, you get gold metal, and here zinc acts as the reducing agent. Now you can say that this is a redox reaction because both oxidation as well as reduction takes place in this equation. And you can see here this is an oxidation reaction because Au in this equation gets oxidized to Au plus. Here the charge of gold is plus, Au plus. Now in the second one it's a reduction equation because Au plus in this gets reduced to Au. So you can prove that or justify that the cyanide process or leaching of gold or silver is a redox reaction, and zinc acts as the reducing agent. Now next let us see the extraction of copper. Extraction of copper. And copper is extracted from its ore, copper pyrite, and the formula is CuFeS2. Extraction of copper from copper pyrite. So the first step in the extraction of copper will be roasting because it's a sulfide ore. So CuFeS2 is heated in a regular supply of air when copper is produced in the form of copper matte. Copper matte, and this copper matte is a mixture of Cu2S plus FeS. Then Cu2S then undergoes roasting and it gets converted to oxide. Same way FeS also will get converted to oxide, and finally it is removed. FeS is removed. FeS is actually the impurity present. We don't want FeS. This is the extraction of copper. So first reaction is roasting, and you can see here the equations for roasting reaction. This is CuFeS2, that is our copper pyrite, plus oxygen, heat. You get copper matte, Cu2S plus FeS. Copper matte is a mixture of Cu2S and FeS, plus sulfur dioxide gas is produced. Now in the second step, Cu2S will combine with oxygen to form Cu2O, and FeS is getting removed in the next step. So this is the first step, roasting. Now the second step is smelting, and the various reactions taking place in smelting process in the extraction of copper is written, and here in smelting you can see the FeS produced will combine with oxygen to form FeO plus SO2. Now this FeO, I told you FeS is our impurity. So first FeS gets converted into FeO. FeO will combine with silica. Silica here acts as a flux to form iron silicate, which is our slag. So removal of FeS as FeSiO3. Now the other reactions are, so FeS is removed, now we have Cu2s and Cu2O. So Cu2s will combine with oxygen to form Cu2O, that is oxidation of Cu2s. Now next is Cu2O, this is auto reduction method. Cu2O plus Cu2s will give copper metal plus sulfur dioxide gas. Again Cu2O will undergo reduction with carbon to get copper metal and carbon monoxide. So these are the two reactions where we get copper metal, that is one is auto reduction of Cu2O, then the reduction of Cu2O using carbon. We get copper metal. Now you can see that the copper extracted by this method has a blistered appearance. That blistered appearance is due to the formation of sulfur dioxide gas. That sulfur dioxide gas will give a blistery appearance to copper. So this is copper is also called blister copper. Now the refining method used for the purification of copper is electrolytic refining, which we have already discussed. Now there is one more method for the preparation of copper, that is extraction of copper from low grade copper ores. Low grade copper ores we can extract copper, that is a leaching method. Now low grade copper ore is leached out using bacteria or acid in presence of air when copper goes into solution as Cu2+. So the equation here is Cu plus 2H plus half O2 gives Cu2 plus H2O. Now the solution containing Cu2 plus is then treated with scrap iron or hydrogen. So reduction takes place to Cu2 plus. So the equation with iron is Cu2 plus iron gives Cu plus Fe2 plus. We know that iron is more reactive than copper, and reaction with hydrogen is Cu2 plus hydrogen gives Cu plus 2H plus. So this is how we get copper from low grade copper ores. The first step is leaching of copper, low grade copper using bacteria or acid in presence of air, and copper goes into solution as Cu2 plus, and second step is reduction of Cu2 plus using iron or hydrogen. So this is the extraction of copper. So with this we finish all the extraction of metals. Thank you.